Hey, welcome back. This is now inverse functions, and they're pretty simple. There's some issues with domain and range again, though. That can be a little bit troublesome. You're probably not used to it. It's only because you're not used to it. Once you get used to it, it's no big deal. But it's not something they deal a lot with in your algebra class. So probably that last section was kind of a lot to stomach. But anyways, inverse functions or functions that kind of undo operations. For example, let's say I have 3 and then I multiply it by 7. Okay, so 7 times 3 gives me 21. The inverse function will undo that and bring me back to where I started. So how do I undo multiplication? Well, you do division, right? So we'll take 21 and instead of multiplying it by 7, we divide it by 7. Okay? And of course we get back to 3. Okay, so if the original, we could make these into functions, right? So we could say first the original thing, f of x, was to multiply whatever we put in by 7, right? So we do another number, right? Maybe 5. And then we multiply it by 7, and we get 35. And then to undo that, we divide by 7, right? So 35 divided by 7 gets me back to 5. Okay, so the first sort of operation we did was to multiply the given number by 7, so 7x. And then the second operation, in order to undo it, we'll call that g of x, we divided by 7. So we took sorry, let me erase that. I've lost my eraser. There it is. What did we do? We took the result, whatever, x, I'll call it, and we divided by 7. Okay. Okay. And these turn out to be inverses of each other. Okay. And you could tell because of this, what they call the cancellation effect. If you put one inside the other, you end up where you started, you end up with x. Okay. So the cancellation effect. That's when I do a composition, f of g of x, and I end up with plain old x. So let's make sure that works for our case, right? So I have f of g of x. What is that? So wherever I see x and f of x, I'm putting g of x. So 7 instead of times x, it'll be x over 7. And then 7 times x over 7 is, okay, it works. And the other way around should also work if they are inverses. Okay? So let's try g of f of x. Okay. So this time, wherever I see x and g of x, I'm putting 7x. 7x over 7 is x. So when that happens, when the cancellation effect is working, you'll have inverse functions. And we could say g of x is the inverse of f of x. And rather than writing out is the inverse of f of x, we have notation for it. And it looks like this. F with an exponent of -1 of x. Okay, and that's not like, 3 to the -1 is 1/3. That's not what we're talking about. This is just a notation which just coincidentally looks like an exponent. Okay, but when you put it on a function like that, it doesn't mean to, it's not the same as 1 over f of x. Okay, so anyways, let's make this more rigorous and put it into a definition. Suppose f of g of x equals x, and this is where we have to deal with the domain stuff, for all x in the domain, and I'm going to write domain as d, and then which domain, I'm going to put that in the subscript. So f of g of x equals x for all x in the domain of g, and g of f of x equals x for all x in the domain of f. Okay, if those two things hold,
then g of x is the inverse of f of x. Okay. One nice thing that also we get for free here is that a statement about the domain and ranges. Also then, the domain of f is going to be equal to the range of f inverse. And then the range of f is equal to the domain of f inverse. Okay. So in general, if you could figure out the domain of one, you'll have the range of the other. And that's helpful when they're calling upon you to determine the domains and ranges of the functions, which they will. Okay, let's look at some exercises. So they want you to determine the compositions and then state whether or not the functions are inverses. So, example, they give us f of x is 4x plus 9. And then g of x is x minus 9 over 4. Okay, so I want to look at f of g of x. And so I'm plugging in g of x and the f of x. So that would be 4 times x minus 9 over 4 plus 9. 4's cancel on that. You get x minus 9 plus 9, which of course is x. The other guy, g of f of x. And of course, this will work for all x's in the domain of G. The domain of G is all real numbers. Okay, there's no issues with division by 0. The domain of f is also all real numbers. And this process we did for f of G of x, nowhere in it was it a problem to have any x value substituted in it. There's no division by 0, no roots. Okay. G of f of x, I'm going to put f of x in for x, 4x plus 9 minus 9 over 4. This will be 4x over 4, which will equal x. So these two functions are inverses. So we have verified the functions are inverses. Okay. Okay. So how would I find an inverse rather than just having it thrown in my lap, like in this previous example? It's pretty easy. You just swap the x and y's and solve, right? Usually pretty easy. Sometimes it's very difficult. But anyways, in general, swap x, y, and solve. Okay, so let's look at an example. F of x is 2x plus 3. So y is 2x plus 3. Swap the x and the y. Okay, and then solve for y. Okay. And those guys are inverses of each other. You should check the composition. I believe that's what they do in the book, but usually if it's easy enough, you don't have to worry too much about it. Let's look at another example. There's no square roots or anything, you're probably okay. X plus 4 all over x minus 2. And we need to kind of note the domain here. The domain of f is going to be all real numbers except 2, right, where the division by 0 would happen. 2 union with 2 to infinity. Okay. So let's get the inverse. So I'll replace y with x. So I'll have x equals y plus 4 all over y minus 2. This one's a little more difficult. I have to multiply both sides by y minus 2. On the left-hand side, I'll distribute. So I'll have xy minus 2x. On the right-hand side, the y minus 2's can be removed, and you get y plus 4. I want to collect all the y's on one side. So I'll have xy minus y equals 2x plus 4.
Then I could factor out a y. So I have y times x minus 1 equals 2x plus 4. And then divide by x minus 1. So y equals 2x plus 4 divided by x minus 1. Okay. And clearly the domain of this thing is, which we call G, I guess, everything except 1. Negative infinity to 1, union with 1 to infinity. Okay. So if you're going to check these, f of g of x, to make sure that they are in fact inverses, you just have to make sure that when you're working with f of g of x, you take into consideration the domain of g. Okay, so the domain of g is negative infinity to 1, union with 1 to infinity. And so in this case, f of g of x, what is that? It's wherever you see x, put g of x. So I have 2x plus 4, it looks like a monster, all over x minus 1 plus 4, all over 2x plus 4, all over x minus 1 plus 4. And then you would simplify this. For it to work, we need to make sure that this entire thing is not 0. Right? Maybe that's an issue you may wonder about. And it's not really an issue, is what I'm going to say. For the domain of g, we don't have to worry about the x minus 1 in that denominator. We don't have to worry about this part. Sure enough, that won't be a problem because we excluded 1 from the domain. But the whole thing, you may still be scared that this entire thing, if it equaled 0, that would be an issue. Okay, and the cancellation equations would kind of break down. But I'm saying it's not, and you could tell if you set it equal to 0. So usually it's not an issue. So it's a rational equation. Multiply everything by x minus 1. So x minus 1 on the left and the right. When I distribute here, the x minus 1s will cancel in the first part. You get 2x plus 4. And then plus 4 times x minus 1. Oops, it should be 2, right? Minus 2 in the denominator. Sorry about that. So this would be minus 2. Okay, and then that would be minus 2. Sorry. So negative 2 times x minus 1, and on the right-hand side you have 0. So it would be 2x plus 4 minus 2x plus 2 is 0. And the 2x's cancel, and you get 6 is 0. In other words, it's never equal to 0. There's no solutions to that thing. So long as you get x out of it, there's not going to be any issues with proving that they are inverses. And if you go, let's go through the math on this one just so I could show you what it looks like. And I'll multiply top and bottom by x minus 1, okay, to get rid of the complex fractions. So for the first part in the numerator, you'll just end up with 2x plus 4 because the x minus 1s will cancel. And then plus 4 times x minus 1 all over 2x plus 4, and then minus 2 times x minus 1. And then that'll be 2x plus 4 plus 4x minus 4 all over 2x plus 4 minus 2x plus 2. And then that'll equal 6x all over 6, which is equal to x. Okay. Let's do the other one just for the sake of completeness. You can fast forward the video if you don't want to see it. But, for those of you who do, we'll have 2 times x plus 4 all over x minus 2. So now I'm plugging in f of x into g of x, okay, and then plus 4 all over x plus 4 all over x minus 2 minus 1. Multiply top and bottom by the x minus 2. Okay. So for the first part,
the x minus 2's will cancel, and you'll have the 2 still there. So it'd be 2 times x plus 4. And then plus 4 times x minus 2. Downstairs, when I multiply by x minus 2, in the first distribution, the x minus 2's cancel, leaving you with x plus 4. And then the second distribution, minus x minus 2. Okay. And this is great practice. I've been telling my calculus students, 90% of calculus is just algebra. And it's this kind of stuff, this kind of work is going to make you really good at algebra. Okay, so make sure you're doing your homework. X plus 4 minus x plus 2. So in the numerator, I'm getting 6x. In the denominator, I'm getting 6. And so that's x for all x in the domain of f of x. It'll work. Okay, right. Consider this next example. Y equals x cubed plus x minus 1. Try to find the inverse. You can pause the video and see if you have time. Pause the video and try to find its inverse. So try the swap and then solve for y. Okay, so if you paused and you tried to solve, no, I don't know how to do that. I can't figure out a way to do that personally. There might be some archaic method. There's something called depressed cubics. You can Google that and maybe learn something about factoring those things. But for most of us who haven't been good mathematical historians, I don't know. I don't know how to factor that. I don't know how to solve it for y. Is there even an inverse? Okay, I don't know how to solve it. Know how to find the inverse. Okay. Does an inverse even exist? So one of the problems with being a math person is sometimes you're asked to find a needle in a haystack. The problem may be that you don't know if a needle is actually in the haystack, and that is a nightmare scenario. So considering the question, does an inverse exist, is important. May not seem like it helps, but it's that idea. You know, the difference between looking for a needle in a haystack, knowing whether it's there or not. That's the issue. So to figure out if an inverse exists, we have something like the vertical line test. It's called the horizontal line test. And what it's looking for are these things called one-to-one functions. Okay, so if a function is one-to-one, that will imply it's invertible. So one-to-one functions are invertible. So if I could prove this thing above is one-to-one, then it'll be invertible. Basically, algebraically, if you find that two y values are the same, so if f of x1 equals f of x2, then it must be the case that x1 is equal to x2. Okay? If you remember the arrow diagrams we had, okay, way back in the beginning when we were talking about relations. So if you had something like this, there were relations and then there were functions, right? So this guy is a relation, but it's not a function because of that first value in the domain. This particular x right here is going to two different y values, so it's not a function. We want two things. We want something to be a function, and we want it to be one-to-one. So this guy right here is a function, but it's not one-to-one. Okay? This is a function because for every value in the domain, every x value goes to one and only one y value, but it's not one-to-one. And it's because you have
two y values here that are the same that originate from two different x values. If you look at these two diagrams, compare and contrast the first diagram here to the second diagram here. How are they similar? Well, one is just kind of the reverse scenario of the other. And so one-to-one means it's a function kind of in both directions. Okay, so in the range, if you considered that to be the domain, this guy would cause it to not be a function because it's going to two different sort of y values. Okay, so in that direction, it's not a function, and that's how you could tell it's not one-to-one. So something that is both one-to-one and a function is very, very well behaved. It's basically, every one thing is going to one thing. Maybe there's some mixing, but nothing really crazy. Okay, so this last example is a function, and it's one-to-one, so therefore it's invertible. Okay, so the horizontal line test is probably what most students will use to determine if something is one-to-one. Later, we need more rigorous methods because graphs can lie. Okay, but anyways, for now, we can do like a horizontal line test, which is just like the vertical line test that we had before, except now the lines are horizontal, right? So, okay, horizontal line test. Some of our favorite functions are not invertible. So, example, y equals x squared. F of x equals x squared. So it is a function. It passes the vertical line test, but it's not one-to-one because it fails the horizontal line test. Okay. What about those cubics, like that one I was looking at above? Well, usually for something like that's really simple, I mean, cubics can have humps in them, so they may not be one-to-one, but something simple like x minus 1 cubed will be. So how do I get x minus 1? Well, x cubed, if you recall, kind of looks like it has this weird S shape. Okay. Looks like this. And then to get x minus 1, all we have to do is shift that to the right by 1. And then we get this. Okay. So there it is. And that thing passes the horizontal line test. So any horizontal line will hit it at most in one place. And so therefore it is one-to-one, and therefore is invertible. Okay, so the problem is finding out what is that inverse function sometimes. Anyways, we can make things like this invertible, right? So if you go back to where I kind of was starting, how do I go? Okay, so first I begin with 3, and then I square it. So I'm using this squared function, right? F of x equals x squared. So my first function, f of x equals x squared, and I get 3 squared, which is 9, right? To undo it, what do I have to do? Well, you take the square root, right? So the square root of 9 is 3. So f of x, or g of x, our inverse, we think it's our inverse, is the square root of x. It doesn't quite work, though, because the function is not one-to-one. So where does it kind of fail? It fails on negative numbers. So I've had negative 4, and then I square that. I'll get positive 16. And then if I try to undo it, I don't get back to where I started. I get back to positive 4. Okay, so that's the issue. This is a big issue, and to correct it, what we're going to do is kind of exclude all of the negatives or exclude all of the positives. So basically, you exclude one whole half of the graph. Okay, so to make a square root function invertible, or to make a square function invertible, so to make something like f of x equals x squared invertible, variable, we restrict its domain. Okay, and there's two ways to do that. We can just consider this half. Okay, so this is f of x equals x squared, and we restrict the domain to just be the x values greater than or equal to 0. And in that case, the inverse, which you can always draw by just revolving the graph around this line y equals x, the inverse function, which I'll do in yellow, will be the square root function, okay, which is this function. So g of x will be the square root of x. And again, the range is going to be 0 to infinity, but the domain for this guy, okay, thank you, please get out of the way. The domain is also going to be x greater than or equal to 0. So we could do that, or we can, all we need is for the graph to pass the horizontal line test. So we can also take like the other half. So instead we could say, let's take this half. Right? So that's f of x equals x squared, but the x values are less than or equal to 0. Okay? And in that case, when we revolve it about the line y equals x, and I may need some helper points here for me to pull this off. So this maybe is 1, 1, and then 2, 4. To get the points on the inverse, you just take the reverse of those ordered pairs. So if this is 2, 4, we need 4, 2. 2, 3, 4, 1, 2. If this is negative 1, 1, we need 1, negative 1. 1, negative 1, 1, we need 1, negative 1, and then 0, 0. So our result, the inverse, we put it in yellow, is going to look like this, kind of. I didn't draw it very well. It should be symmetrical. If you do your tick marks correct, it'll look a lot better. Okay, so anyways, what the heck is that other thing? That other thing is the negative part of g of x. So g of x will be negative square root of x. This, oh, I see what I did wrong. This should be negative 2, 4. Okay, that'll help a lot. As long as I can get my stupid eraser to work, that will be something better. Okay, so I erase that too. Okay, so let me try that again. This is negative 2, 4, and then my points 1, negative 1, and then 4, negative 2. Okay, so it's down there, and then it'll look nicer. Okay. Right, so in this case, the x values again are greater than or equal to 0. So that's the domain, right? These are domains, but the range is, let's see what the ranges are. Sorry, I'm getting the colors all screwed up. The domains are these, but what are the ranges? So the range should be x greater than or equal to 0. It's just the domain of g of x. And then the range of g of x is the domain of f of x, the x greater than or equal to 0. And likewise over here, so the domain of g of x will become the range of f of x, right? X greater than or equal to 0. And then the domain of f of x will become the range of g of x. And you can kind of see that in the picture. The range of g of x, the yellow graph, is negative values. So the problem is then finding that sort of inverse function. So if you start with f of x equaling, to find this f inverse of x, given f of x equals x squared, there's kind of an issue going on with the solution, right? So you start with y equals x squared, and then you swap the variables. You get x equals y squared. then you take the square root on both sides, right? So you get square root of x equals y sort of, okay? And I say y sort of because we have the square root property going on. If you recall, if x squared equals b, then x equals plus or minus square root of b. So kind of thinking in that way, let's rewrite this problem, right? So we have y squared equals x, or y squared equals x. X equals y squared is the same as y squared equals x. And now we kind of have this, right? So if y squared equals x, then y must equal plus or minus square root of x, okay? In other words, y is equal square root of x, or y is equal to there's two answers here. And the deal is, if you've restricted your domain, you just pick one or the other. So you can notice in the first case, so this is 1, and then this is 2. In the first case, my g of x function is the positive one, the positive square root of x. In the second case, my g of x is that other guy, the negative square root x. Okay, so it's one or the other, and you have to determine which one it is. Usually what I do is by looking at the graph of f of x when it's restricted, and then look at its revolved version, and I can tell if it's negative or positive. Okay, and also from the restricted domain. So if you look at, for example, number 2, the domain of x is going to be the range of g of x. And so if the domain of f of x is less than 0, if it's negative, the output of g of x has to be negative. In other words, you have to go with that negative answer. Okay, okay, so it's definitely an issue, and I'll take a look at an example, one of the examples online there as soon as I get a sec. Okay, so just one last part on graphing. So graphs, to graph an inverse function, you're rotating about the line y equals x. So for example, if we do have one of these kind of square rootish type functions, and we have the points -1, 0, and then the point 0, 1, and it looks like this. Okay. To get the inverse, you just revolve it around that line, that dashed line I just drew. And it'll probably look like this. Okay. To be more careful, what you can do is just take the reverse of the coordinates. So the inverse should have, instead of -1, 0, it should have 0, -1. And certainly that's right here, right? 0, -1. And then instead of 0, 1, it should have 1, 0. And that will be right there. Okay, okay, so sometimes it's not easy to rotate that thing about that line y equals x. And in those cases, just play with the coordinates like I just showed you. Okay? Okie dokie. Let's go ahead then and look at a homework problem. Okay. So I should have one queued up here for us. Let's look at a similar one. Right. So we're given the function f of x. Whoops. Let's get rid of that. We're given the function f of x equals x minus 6 squared. And they're telling us they want x less than or equal to 6. Okay, so what I advise you to do is graph the thing. Use Desmos, or you should be able to graph these by hand, right? So it's x squared shifted to the right by 6. 1, 2, 3, 4, 5, 6. And then this tells you want everything less than 6. So normally here is your x squared graph, right? X less than or equal to 6 means you take this side of it, right? So our original sort of function given is going to be this part in blue, this arm, Okay. Okay, so that means let's go ahead and see if we can get the inverse, which is what we need. So f inverse of x. Let me do it in white as well. So f inverse of x. How do I find that? I need to swap the x and the y variables. Okay, so let me erase this. So x equals y minus 6 squared. Okay, so in the first part, you need to use the square root property, right? So you have y minus 6 squared equals x. Square root of both sides. Y minus 6 is plus or minus square root of x, right? And then I can move the 6 over and I get y equals 6 plus or minus square root of x. And I have to figure out which one it is. Is it y equals 6 plus square root of x, or is it y equals 6 minus square root of x? And the range of this inverse function is the domain of the original. Okay, so the range is this x less than or equal to 6. So let's look. We know the range must be all the numbers from negative infinity to 6, right? So which expression will give you these numbers? Is it the 6 plus something or the 6 minus something? Which expression, when I put in values for x, will give me numbers less than or equal to 6? Well, you could try it, right? You could say, let's let x equal 4, right? So y equals 6 plus the square root of 4 is 6 plus 2 is 8. Is 8 in that range? No, it's not. Okay, so we're going to be using this piece as our inverse. Okay, so f inverse must be the 6 minus square root of x. And then x is greater than or equal to, well, that's going to be the range of f of x, right? And the range of f of x is x greater than or equal to 0. And I just found that by looking at the graph. Okay. So graph the two in the plane. So if you want to, you can get some coordinates and then flip the coordinates, right? So we have 6, 0, and then we have 5, 1. Okay, so we should have 0, 6, 1, 2, 3, 4, 5, 6, and then 1, 5, 1, 1, 2, 3, 4, 5. Okay, and we're doing this rotation about this line, so it's going to look like, I believe, this. Okay. And then we just look for the graph that looks like that. So it looks like A. Use interval notation to give the domain and the range. Well, the domain is given, so that's easy enough. It's just 6 to infinity. So, or negative infinity to 6, sorry. So it's negative infinity, there's a button for it, to 6 with a close bracket. And then the range 0 to infinity. So you could look at the domain of f inverse, which starts at 0 and then goes to the right. So 0. So I usually use the graph to kind of figure these out. Okay, 0 to infinity. Okay, so yeah, more of the same. For this one, it's not so hard. Let's go ahead and do this one because you're not going to have to worry about a restricted domain. If you have like an odd power, it's not an issue. Okay, you don't have to worry about it because it's going to be 1-to-1. And so for f inverse, if you have f of x equaling x cubed minus 2, you know, so x would be y cubed minus 2, and then y cubed equals x plus 2, and then you take the cube root on both sides. Okay, so you have the cube root of x plus 2 for your f inverse. And to graph them, what does x cubed minus 2 look like? Well, you're going to go down 2, and then you have this looking thingamajig. And then to rotate that, it's going to look, I don't think I can do that in my head. It's going to look like this. Right? And then the domain and range, it looks like the domain is all real numbers, the range is all real numbers, and etc. They're all real numbers for all of them. Let's see if there's anything else weird in here. Some story problems. Okay, I guess I'll cut the video here then, and thanks for watching as usual, and get in there and do your homework, and I'll see you next time.